So let's continue. Firstly, as we said before, Mr. Rimon certainly right last time, it is possible to put sin u equals 0 at the edges of strings, sorry, wrong statement in the class. And in fact, it's a possibility we use it as we progress in our never-ending languages. Okay, so fine. So let's go on and complete our discussion of open strings and unoriented approach. Okay, there was one more comment from Lognagham's questions last class. Lognagam was asking why don't you do something completely different involving the orientation operator and everything else? Why does it have to be the orientation protection and an already obtained closed? And I think that the answer to that goes more or less like this. You see, you remember what constraints we got from the closed string set in constructing closed string theories. Our constraints came from closure of the operator product expansion, which we will demand to be true no matter what. They came from mutual locality of correlation functions, which we will demand to be true no matter what. And we got one additional piece of we used one additional piece in input, and that was that we wanted a modular variant partition. Actually, we used very little of that, but we used that. Now, you see, as we have seen, when we introduce an orientation reversal into the theory, what that does is it introduces new kinds of Riemann surfaces in, let's say, one graphs. But the torus remains present, and that object we will always demand to be modulated. Just because it makes no sense to integrate over the torus subjects. And the torus is independent of just has no orientation projection operating. Okay? So, just that, the modular invariance of the torus diagram, irrespective of what else is happening, okay, fixes what happens in the closed string sector without orientation projection. And that leaves us with basically only two possibilities, type 2 and type 2 theory. And then if we want the orientation projection, that basically type 2 theory is the one that's okay. Now, we could try to do more exotic things, involving not just orientation, but something else also. And we will do the analog of one of these things and say the hypnotic string. I mean, there's no claim here that, you see, that we made all consistent constructions of anything. Because that's really limited by imagination. These are the consistent constructions that we, in the class that we're playing on. Of course, I will see later, as some of you already have seen research work, but as you'll see more as we go around this course and read more about string theory. String theory has this nature about it that if you take any one part of the subject and study it deeply enough, you often end up encountering other parts of the subject. Okay, through duality or something, encountering it in some way or another. And the fact that through the intensive study of string theory over the last 20 years, we've not chanced upon somehow or the other some other weakly coupled part of it. Something else that looks like it's described as other weakly coupled string theory. I think it's the best reason to believe that we have actually constructed all the weakly coupled string theories that exist. So within the class that we've talked about, we've given arguments that we've done. But how do you know that this is something totally different? It's very hard to be sure that that is not true. But it's this nature of string theory that now it's just a matter of belief. But it's this nature of string theory that, for instance, suppose we hadn't constructed the hypnotic string. Then by doing it, by trying to understand the strong coupling behavior of the type 1 theory, we would have realized there was another weakly coupled theory, and then we're forced to construct it. Okay? We see this. So we've not encountered any such incompleteness so far. I think that is the best reason to believe that the things that I'm presenting here is the complete list of weakly coupled string theory. Though who knows, there could be surprises. Okay.
So why should the torus diagram by itself be modulated?
Why should the torus diagram by itself be modulated? You see, because in string theory we are instructed to sum over all conformal, all inequivalent surfaces. Okay? So if this thing was not modular invariant, there would be basically you would be asked to sum over more than all conformally inequivalent surfaces. There would be a large diffeomorphism anomaly.
Okay, I understand why you need a modular invariant for the whole.
Why do you need just? You see, the rules of string theory say.
Okay, we did achieve modular invariance, for example, by apart from the NSNS sector, the modular invariance that the other sectors are achieved by summing over.
Right. So we would need something else that has the structure of a torus. There's nothing else that has the structure of a torus. Right? Because any diagram in which you impose, in which you put one of these orientation preserving things, has a different topology. So it could be that many different torus diagrams sum up to give you something more. Okay? But how can summing, let's say torus with a Klein body give you something more? It doesn't depend on the same module. Right, so the sums over tori should give you something. Because that's a sum over any given topology should be by itself. That's the okay. Good. Other questions, comments? Fine. So, let's return to our study of the open string. We talked about the open string last time, and we talked about when we motivated the claim that the open string, this guy goes into y, this is 0 to t, needs to be studied in both the Riemann and the Nebel-Schwarz sectors, and needs to be studied with the GS distribution. So, we're going to be computing now the diagrams that we computed last time for the unoriented bosonic string. So we want to start computing them one by one now for the superstring. So let's do this again. Okay. So we will first concentrate on the cylinder diagram. There will also be a diagram like this with an orientation reversal projector in it, but we'll deal with that later. Okay. So let's first look at the cylinder diagram. So the cylinder diagram has you remember our discussion of the open string. The two possible boundary conditions at the two ends translated into the two possible sectors for the double string. There was the Riemann sector and the NS sector. Okay? And the minus 1 to the power f is just the minus 1 to the power f that we talked about before. So this is now really simple. It's like the square root of what we did for the closed string. Okay? So what do we have? So we have z, if you remember our notation last time. So we have z0, which is the nth sector. Okay? And 0, which means ordinary trace of I times t. Okay? Plus minus times z0, which is the ns sector, times z1, which is minus 1 to the power f, of I times t. Okay? And then we'll have, in addition, z, so far we dealt with the ns sector in the double theory. Okay? So, in addition, we have the Riemann sector, and the Riemann sector contributes with the minus sign. This is the usual spin statistics business that we talked about at length for the closure. So, we'll have minus of now z1, which is the Riemann sector, and 0, which is the ordinary trace of I times t, and then in the convention that 2b imposes minus 1 to the power f is equal to 1 minus 1. We will have plus z1, which is the Riemann sector, times 1, which means traced with minus 1 to the power f. And then this thing will contribute to the whole sum with a factor of 1/4. the half is because of the half of the projector 1 plus minus 1 to the power f, and the other half will be in the half from the projector 1 plus omega. This is just one of the terms in the orientation. Okay? So this is the answer in terms of functions that we know, because we studied that in detail when we were doing the partition function, when we studied the partition function of the closed function. Is this right? Okay. Now, what we're going to do is to try to look at the modular transform of this object, just like we did when we studied the cylinder diagram for the boson extreme. Now, we're going to separate out those diagrams that we're going to separate out the contribution. You see, the cylinder is made up of two ends. Okay? Each of its two ends is a source for all kinds of massless fields. In particular, the edges of the cylinder source NS sector massless fields and Raman sector massless fields. Now, as we've seen when we studied deep rays, the cylinder diagram can be roughly thought of as the force that you get due to massless open string, massless closed string exchange. Now, it could be, and it is true, as in the case of deep rays, this again we studied, that the force from the graviton exchange cancels the force from the Raman exchange. Do you remember that when you studied the force between deep rays? However, if you, and this is the consequence of supersymmetry. Okay? However, if you were interested in computing the tension of the deep ray, what you did was to look at the part of the closed string exchange diagram that came just from NS-NS exchange. So just from the dilaton graviton sector. And that allowed you to compute the tension. The fact that it balanced the charge was sort of irrelevant. Okay? Do you remember this from the problem you solved in detail in your exam last class? Last year. Well, that was boson extreme. Oh, you didn't even have that. Sorry, you just had that. Sorry, if you did the same thing in the superstring, you're going to have. Sorry, sir. Okay, yes, you would have the same thing with the Raman ray. So, okay, I should not remember it. You don't know. But here we're going to see this in great detail. We're going to see that the cylinder diagram has closed string exchange both in the NS sector and in the Raman sector. You see, now, the problem with a tadpole is that you've got a linear source term for a massless field. If by convoluting over two such tadpoles and summing over all tadpoles, you happen to get 0, that doesn't help you. Okay? That doesn't help you. So what am I going to say? I'm going to say that these cylinder diagrams, you see, the diagrams that we compute will often be, when we sum over them, 0 because of some sort of supersymmetry. Okay? Nonetheless, the theory should have no tadpoles for massless fields. That is the condition for consistency. Right? You should just not have a source for any massless field. So it's not enough that we get 0 by summing over these diagrams. We need to get 0 for the tadpoles for individual massless closed strings, and in particular, the cylinder diagrams, the part of the cylinder diagrams that comes from NS-NS exchange, and the part of the cylinder, the divergence in the cylinder diagram that comes from massless NS-NS exchange, and the divergence in the cylinder diagram that comes from massless Raman exchange, should individually vanish. Okay? Because otherwise you have a problem in your theory, though it may happen to cancel out in the one loop diagram. You would have a problem, for instance, if you changed your source a little bit so as to change the contribution of NS and Raman sectors. But more fundamentally, there's just a tadpole in the disk diagram with the insertion of an NS-NS massless potential, which tells you that you don't have a stable diagram. and you don't have a stable background. Right? Remember the problem with the source for master speed is that if you took del 5 over t squared in your dungeon and you add it to lambda times 5, there is no vacuum that is translationally invariant. So, no matter how small this lambda is, it completely destabilizes the vacuum, completely destabilizes the symmetries of your vacuum. So just, there is no translation invariant theory, a vacuum in the theory. Okay, so tag codes for master speeds are just unacceptable. Okay, so the condition that we're going to impose here is that the tag codes have to vanish separately due to NS-NS exchange and Riemann exchange. Actually, we should impose that they vanish separately for each particular participating master speed. Well, that will turn out to be true in the situation where we don't stand it ourselves. Okay, so now what we want to do is to isolate out the contributions of when we move to cross channel, the contributions of masters NS-NS exchange, isolate them out from masters Riemann exchange. But that's very easy. You see, because each of these things is represented by path integral. The path integral has the fermions either periodic or anti-periodic in this direction. It's anti-periodic if there's a 0 here, and it's periodic if there's a 1 here. So the path that comes from, that represents NS-NX, masters NS-NS experience, comes from this guy. Okay? So the term that we will focus on, masters NS-NS exchange across two channels, is Z00 of T minus Z10 of 1. Okay. Now what do we do with this stuff? We want to isolate the contribution of the master set. Okay, the divergence in this diagram comes from running of master states. So we should modular transforms. Okay? We should of course multiply this by the contribution from the bosonic string and modular transform. But that's very easy because we've already learned how to modular transform these functions. Okay? So the modular transform, so we just apply the rules that we had in the previous class. The rules were essentially that these two guys get exchanged and T goes to 1 by T. So okay. So now I'm going to just add E. Okay. So firstly, let me do this. So Z00 of IT, so that's good. And that will get Z. Yeah. So all that will happen is that this will get flipped here, this will get flipped here, and we bring this guy down. Okay. There were all kinds of anomalies in the tau goes to 1 by tau modular transformation properties of these functions, which we have to look at, which we were very careful about. Okay. But there were no anomalies in the tau goes to minus 1 by tau. So here we can just keep the rule. Okay. So this guy will just become it goes to 1 by 4 and Z00 of well, I'll just say that T goes to 1 by 4. Z00 minus Z10. Z0. Okay. Now, in addition, we should be multiplying this whole thing by whatever we had from the bosons. So there was an eta to the 8 factor, and there is the part that comes from the bosonic 0. So there was a 1 over T to the 5. Okay. Now we process this diagram exactly as now we process this quantity exactly as we did for the first. Okay, that is this eta to the T factor. We modular transform that. That eats up 4 of the 5 1 over T factors from the 0 point. There is an additional 1 over T factor left, that combines with the integral over moduli space dt over t, gives you dt over t squared. But then defining 1 over t is s, you get a ds. Okay? So, in the end what you get integral ds, this object, times this eta, everything is function of s, eta to the power 8 in the schematic. Okay, no remaining factors of t or s. Okay, so let's write this as a function of s, where s is not. Is this clear? Each of the 8 because the 8 goes up. No, z00 is just the partition function over the vertex. It was and the z0. I'm sorry. The z00 should be to the. You remember we made the we complexified the fermions. Z00 was partition function over everyone. Okay, fine. So now this is not right. Is that clear? Okay. Now up to factors which, unlike for the bosonic string, may not really keep track of carefully. Just the factors work exactly like the bosonic. The factors of 2 are all that's important. I'm not really keeping track of them. They work exactly like that. Up to factors disappears. So now let's first look at the problematic ones. You see, this thing should represent closed string exchange. So now the first thing to ask about is what about the tachyon? What about the tachyon? The bosonic string, we always had a closed string tachyon, which gave us trouble. So we always promised that would go away when we look at the when we start studying the superstring. So how does that work? So firstly, where does the tachyon come from? The tachyon comes from the fact that this eta to the power 8. This eta to the power 8 has a q to the power minus 1 by 3 in it. 1 over eta to the power 8 has a q to the power minus 1 by 3. Because 1 over eta has a q to the power minus 1 by 4. Okay? Now each of these guys are fermions in the NS sector. Because these zeros are top. So they each contribute to 0 point energy. They each contribute to 0 point energy also, which changes this q to the power minus 1 by 3 to q to the power minus 1 by 2. Okay, you could look up what the 0 point contribution is from Z00. I quoted. We worked it out. But from Z0 anything, it was q to the power minus 1 by 4. Okay, so we had 4 powers of q to the power. So we have 1 by 6. So 1 by 3 plus 1 by 6 is 1 by 2. Okay, so you have this q to the power minus half, and then the pure oscillator sum. So what is this oscillator sum? Just remember, it's the NS sector with no minus 1 to the f. Okay? So we have product R belonging to integers plus half of 1 plus q to the power r. What was this product? It was minus product R belonging to integers to the power, integers plus half, once again, because we're still in the NS sector. But 1 minus 1 to the power R. No, 1 minus q to the power r. Because every fermion contributed with the negative sign because of the minus 1 to the f in the trace. function, this whole thing is to the power 4, this whole thing is to the power 4, and then the eta function is to the power, is product 1 minus q to the power r, the whole thing to the power 8, where r now belongs to integer. Now, why did we have problems with the tachyon in the bosonic string? In the bosonic string, we had problems with the tachyon because this q to the power minus half, when was e to the power s times t, and so integrated over s gave us a divergence of large s. But now look at this. Let's Taylor series expand this function. The term with q equals 0 is 0. So 1, we get 1 minus 1. That's just minus sign. You know, point from all states and the trace have to be put in with the negative sign. They represent space time. Okay? So the one term is not there. It's not a surprise. This is just a statement that when we do things correctly, we impose the GSO projection in the cross closed string. And when we impose the GSO projection in the cross closed string pattern, there is no tachyon. It will be seen explicitly. On the other hand, there are massless closed string states. So they should be there, and they are. You see, to get the massless closed string states, we have to get the term that's constant. So the q to the power minus half here has to cancel against the q to the half. This term here, it has the eta function is completely in q to the power q to the integer powers. However, this guy has 1 plus q to the half, and this guy has 1 minus q to the half. Oh, sorry. These are actually to the power of 8. Well, z00 is to the power 4. Each of it represents 2 probabilities. Right. Okay? So, now if we compute what the coefficient of the term that is q to the power 0 here, what will we get? We get 8 from here minus 8. We get 16. Okay? So, you get a term in the that represents an NS tadpole, proportional in some units, because the 16 is very impressionistic since we kept track of all the factors. So proportional in some units to 16. Is this clear? Okay? So, and now, if you were to work this diagram out with the same degree of care that we did for the, actually there's not much more care that you need. You know, you would need to keep the 1 over square root 2 to the power 5, 1 over square root 2 to the power 10 factors from C. In this case, the modular transformation has no factors of 2, because it's just 2 pi to 2 pi. And so, in the conventions that we worked with in the bosonic string, this diagram contributes with a relative factor of 1 over 2 to the 5. So that's even keeping track of all the factors. Okay? So, removing all factors that will be common for everything, there's 1 over 2 to the 5 times the 16. The 16 will also subset. Okay? So, we completed our understanding of what the tadpole is for these problems. Is this clear? Great. Now let's turn to the computation of the tadpole for NS massless fields from the client. So we have to understand what the client model represents in Hamiltonian language. Okay? So the client model represents what? It represents the identification that under the path integral, you do this to this. Now we have to put that into an equation. Okay. So fermions moving this way are left moving. Fermions moving that way are right. Okay? So the identification that is made is like for scalars is psi of sigma at 2 pi at whatever. Sigma and whatever we want to call this guy. Let's call it 2 pi t. 2 pi t. Is identified with psi bar 2 pi minus sigma. Now, in the expression where we have a trace, where this thing represents a trace, this identification for the usual reasons will have a minus sign. Usual reasons, right? Fermions will have a minus sign, and but this minus sign could become a plus if there was the thing with a minus one. Yeah. Okay. And similarly, we would have. Okay, so let's put this times. So suppose we had. Let's label the sectors by beta and beta bar. I think this is the convention, the notation we use when discussing possible sectors. Okay? So beta is equal to 0 in the NS sector and 1 for the Raman sector. What am I saying? Sorry, beta. I want to say where do we had minus 1 to the f? Okay, sorry. With the with the line watches we have beta and beta bar. Okay, so the beta is equal to 0 if there's no minus 1, and is equal to 1 if we have a minus 1. Similarly for beta bar with f replaced by f bar. Okay, so then we would get this with a minus and an additional factor of minus 1 to the power of 6. Similarly, we will have the equation psi bar sigma phi t is equal to minus 1 times minus 1 to the power of beta bar times psi of 2 pi sigma. Okay, so these are boundary conditions under which we will do our path. Now we're going to use these boundary conditions for only one thing. That is to figure out what sector, what diagrams represent NS and S exchange, what diagrams represent Raman exchange. Okay, so in order to do that, let's look at the boundary condition on the psi field. Let's look at the boundary condition on the psi field as we go over length 2 pi to 2t. Okay, so put this together with this. That gives you psi of sigma into 4 pi is equal to these minus 1s cancel. You get minus 1 bar beta plus beta bar. Minus 1 beta plus beta bar and psi of okay. Now this 4t is a reflection of the fact as we've seen before in the cross channel this diagram gets length 4 pi t and this becomes pi. Okay? So this quantity, this equation here is telling you what the psi field has, what periodicity conditions the psi field has as it goes around this side. Okay? So we learn that in the cross channel, close to the cross channel are propagated in either the NS or the Raman sector, depending on whether beta plus beta bar is negative or positive. Okay, so if we want to focus on closed string exchange in the NS sector, we should look at these diagrams with beta plus beta bar being negative. So with one insertion of -1 df, with the insertion of -1 df either for left movers or for right movers. Okay. So now let's compute this. And by the way, whether this guy is moving the NS sector, this happens both the Raman sector and the NS sector as far as the open string channel goes. See, the boundary conditions for cross channel are determined just by beta and beta 1, and insensitive to what sector you were in the open string channel. Okay, so the contribution to NSN exchange will have two terms. It will come from NS sector exchange, so the NS sector partition function in the open string channel with an effective -1 to the f, and the Raman sector partition function in the open string channel with an effective -1 to the f. By effective -1 to the f, I mean one of the two sides, left or right movers has -1 to the f and the other one doesn't. Both these contributions, which one doesn't matter, it's the same number. Okay, good. So now, what we have to do is to compute these two one loop functions. So that's very easy. Let's look at the NS sector. Let's look at the NS sector first. So, what is the effect of this orientation preservation operator being inserted into the trace? As for the bosonic string, what it does is just identify left moving and right moving oscillators. By the way, of course, it identifies left moving and right moving oscillators. Now, of course, that can only work if the left movers are in the same sector as the right movers. So the left movers and right movers have to be in the same sector, and these things are identified. Okay. As for the bosonic string, the identification just doubles the energy contribution from each oscillator, because you get the same energy from left movers and right movers, and then they're identified. So what you get from the NS sector, the open string NS sector, you get product or belongs to integers 1 minus 1 plus q to the power 2r plus the whole to the power 8. Excellent. And there's a 0 point energy, which when you calculate is left the constant. Okay, this is the part that comes from open string NS. Now, is this completely clear? Actually, there's one thing here that may not be completely clear. The issue of signs, but I'll let you ask. First, you then think about it. The Ramon sector is also of course very similar. Its product or belongs to Z. Now, you see, why was this? Okay, somebody tell me, why was it 2 R2 squared? Somebody? What are the energies of states in the NS sector, of the fermion oscillators in the NS sector? Half, 3 by 2, 5 by 2, and so on. You double those energies, what do you get? 1, 3, 5. That's 200. Why do we double energies? Because the state in the left moving and the state in the right moving sector have to be the same. So what do you get in the Ramon sector? You get, okay, somebody? 1 plus Q to the power. What? 2R. Exactly, because in the Ramon sector the energies are 1, 2, 3, 4, 5. You double them, you get 2, 4, 6, 8, 10. Okay? And then you have to worry about the 0 point energies. Right? And as usual, the Ramon sector contributes with the minus sign, and because of the 0 modes, you get this factor of 16. The 16 is 2 to the power 4. There are 4 pairs of fermions, each of which has a fermionic 0 mode. So that gives you this contribution. Okay? Now, this sounds like a very plausible answer, but you have to be a little careful. Yeah, that's correct. But you have to, in getting it, you have to be a little careful about keeping track of signs. There are 2 signs here that I didn't talk you through. One of these signs is the following. Suppose you've got a state which is A1, A tilde 1. A1 is, so A minus 1, A tilde minus 1. So A minus 1 is the creation operator for left movers, A tilde minus 1 is the creation operator for right movers. Now I apply the orientation reversal on this. Orientation reversal on A1 gives me A tilde minus 1. On A tilde minus 1 gives me A1. So I get the same state up to a minus. The second thing that I didn't talk you through was the fact that if you remember, if you wanted NS and S exchange here, one of these 2 betas had to be negative. Okay? Either beta or beta tilde had to be negative. So, we should have a contribution proportional to minus 1 to the power either left moving or right moving fermion. And you look at this formula, you think, well, this looks like you've not got any contribution proportional to minus 1 to the power fermion. And you've not been careful about taking back these exchange signs. The great thing is that they cancel it. If you just play around with them with sample states. Okay? So, the simplicity of this formula hides the cancellation of signs. And that's true whether we're in the NS or the Okay. So now, up to that subtlety, which I encourage you to play around with to check for yourself. Okay? Up to that subtlety, we have our partition function. And now we want to sit and use it in particular modular transforms. So let's combine it together with the part of the partition function that came from the bosons. So as before, the advantage of not keeping track of numbers is so careful. So as before, we had dt by t, then we had 1 over t to the 5, we had 1 over eta to the power 8, and then we have this times this. Okay, now this we should identify in terms that we were familiar. So very succinctly, what we get from a single NS sector with no minus 1 to the power f. So it's Z00 to the q squared. Is that clear? And this is Z01 also. Top 0 says NS sector, bottom 0 says no minus 1. Okay? Top 0 says Raman sector, bottom Z1 1. Top 1 says Raman sector, bottom 0 says no minus 1. Okay, so we would put a Z00, the whole thing to the power 4 minus Z10, the whole thing to the power 4. And that's our answer. Everything here is a function of q squared. Each of these three functions are functions of q squared. Remember, even the eta is function of q squared for the same doubling reason. Meaning for the same identification. Left movers are identified with right movers because of q squared. Okay, so you get q squared, q squared. Now we play our usual modular transformation. Okay, as usual, t to the 4 will combine with this eta to modular transform. We'll give you some factors of 2. Here we do have factors of 2 in this case, okay? So we're not giving back them. Remaining t will combine with this dt by t to give you a ds. These will have simple modular transformation properties in themselves. The modular transformation properties are Z00 goes to Z00, Z10 goes to Z01. So we get something proportional to the S. Z00 minus Z10 over Z over eta. And each of these things will be will be evaluated at S is equal to 1 over 40 for the usual reason. Right? This strip has 4 pi t and pi, so the reach there is 2 pi and 1 over 40. Or from here, because when you do t2, t goes to 1 by t. Next one. Okay? Fine. So if we were bothering to keep track of all numbers, all these things would be very important. But once again, we just want to be schematic and see the physics come out. So we've got something that's very similar to what we had before. Once again, when you expand the 0-point energy terms, and this one is, sorry, once again, when you expand the 0-point energy terms, you have a q to the power minus half, the same sources as before. And once again, you've got, expressions that are very much like what you had before. You had well, basically isomorphic. You had NS sector with no minus 1 to the f, NS sector with a minus 1 to the f. So it's the same expression we wrote down. Same product here, same product here. So this once again will contribute. First, the fact that there's this minus sign here implies that the tachyon, closely tachyon exchange cancels. The fact that the minus sign becomes a plus sign will combine with the orbitals, in particular the massless modes. That's the cancel, gives you a factor of 16. So in net you get the term that's 1 into 0, so no closely tachyon, plus 16 into q. So closely. That's a massless closely exchange. Okay? So this diagram also contributes to the tap code. But the contribution as for the bosonic string, you remember that the cylinder contributed proportion 1 over 2 to the power of 1. Now, what about this thing here? Where did that 1 over 2 to the power 5 come from? The 1 over 2 to the power 5 came from the factors of 1 over square root t, 1 over square root 2 to the power 10 from the 0 mode. That 1 over square root 2 is not here because we did the 0 mode is the closed string. So, also, we get an additional 2 to the power 5 from this modular transformation, actually 2 to the power 4 of that, from the modular transformation into this q square, as we saw exactly here. And an additional factor of 2 in correctly identifying what s is, in changing the measure from dt to ds. Okay, so this thing contributes, like what? In the same normalization, contributes like the algebra is exactly as follows. You see, everything, all these factors of 2 come from 0 modes and from modular transformations involving the integers. There are no factors of 2 in modular transformations from the z's. So the factor of 2-ology is exactly like that. We worked it out in detail there, so I'm just reminding you.
This is just the track of the capital contribution or the overall?
Yeah, I keep track of that.
There was this 16, right?
Yeah, there was a 16 in both. Let's count both of them. You see, because this has its own 16.
Right.
Same, for the same reason. Okay, great. So we completely understood the Klein bottle and its contribution to closed string dynamics. Any questions about it?
Actually, I missed one point.
Yes.
So why did you, for the cylinder, why did you only look at the NS sector out there? I mean, you considered only the tadpole from the NS sector?
I considered only the tadpole from the.
You look at Z00 minus Z01, right? For the cylinder, you also have the R sector where.
We looked at Z00 minus Z10.
Yeah.
Why did we consider this? You see, because we are interested in the contribution of these diagrams to tadpoles in the NS. So we want the states in the closed string channel to be running in the NS. Okay? So that tells us that this bottom index should be 0. Because the bottom index tells us what the periodicity is on the cylinder channel. Okay, this was basically the same thing, both at the same time. Okay, any other questions about Klein? Oh, very easy to talk to us. Fine. So now we're happy. All that remains is to calculate now the Mobius string. Okay? All that remains is to calculate the Mobius string. So let's remind ourselves how the Mobius string goes. So the Mobius string is this diagram. And now we have to understand the projections that are. Yeah, we have to understand various things. Okay. The first thing we should do is to remember the doubling trick. So the doubling trick was that we could associate this field psi, which is equal to psi of sigma in the 0 to 2 pi range. That was equal to psi bar of 2 pi minus sigma in the pi to 2 pi range. So then we had a field that was defined all the way down from 0 to 2 pi. Okay? And this field was either periodic or antiperiodic, antiperiodic or periodic, depending on whether we were effectively in the NS sector or the Ramon sector for the chemistry. Now, orientation reversal is the statement that psi of sigma is to be identified with psi bar of pi. Now we want to know what this identification does to this master field big psi. This double field big psi, which has simple boundary conditions. Okay? So that's pretty simple. That's pretty simple. Because, say, psi of sigma is identified with psi bar of pi minus sigma. But psi bar of pi minus sigma is, so I want, this psi of sigma is then identified with what? It's identified with psi of sigma minus pi. Plus pi. Okay? So if you ask, what does this orientation projection do, this omega operator do to the big psi? Okay? It identifies big psi of sigma with big psi of sigma plus pi. Now remember that it's big psi that was expanded in osmosis. Big psi was expanded as sum over n, alpha n by sigma. Okay? So then this identification, well, what does it do? It sends alpha n to alpha n into the compensating phase, or depending on conventions, e to the power I n pi. Okay, so that's the action of the orientation orientation or reversal operator omega on the oscillators of this big double phase. Now you may have several questions or you may wonder about this. The first thing that strikes you is that in the NSNS sector, n is not an integer. So the phase that you get from in the NSNS sector is plus minus I, and can be plus minus I. Well, always is plus minus I, rather than plus minus 1. Now that might worry you vaguely, and if you think about why it worries you, one of the reasons it worries you is that if you square the orientation reversal, it gives you a factor of -1 rather than 1. That seems to make no sense. Because you take something, reverse the orientation, you reverse it again, it sounds like you should get back the same configuration. And indeed, however, yeah. So, but you see, what you get is a factor of -1 for each oscillator. Now let's look at states. States built by oscillators acting on the vacuum. These states under orientation reversal will change their sign, okay, only if minus 1 to the power f is equal to minus 1. But in the superstring, we are also going to be imposing a projection that minus 1 to the power f is plus 1. So on the set of physical states is omega squares to 1. Even though in this off-shell configuration, our definition of this omega has it squaring to minus 1 in some states. Okay? So we restrict the tension to physical states of physical mathematics operators. Same thing. Okay? Omega will always square to 1 while. So we can use omega square equals 1 when we need to, when we're restricted to physical states. Fine. The last thing I want to say before we start calculation is look at the boundary conditions of the path integral. So, we want to do this path integral under the boundary conditions that, as we've said for this big psi field, psi of sigma and t is equal to big psi of sigma plus phi and t. And later. But that implies that big psi of sigma and 2t, which is big psi of sigma plus phi and t, which is equal to big psi of, oh, that's fine. So in this yeah, now I forgot the factors that we could do here. So we would have some factor which is like minus 1 into minus 1 to the power beta, where beta is where keep track of whether you have a place of minus 1 in the f or not. Beta 0 we have 4. Let me write that down. Minus 1 into minus 1. So we get minus 1 into minus 1 to the power beta. But the great thing is that it cancels when you do it. You get psi bar of sigma plus 2 pi. Again, the fact that something simple happens when you go 2t is the statement that we've understood many times, that if we want to work with the cross channel, this diagram goes to this one, the 2t. This is length, this is 2t. This is the simple diagram of cross channel. And we now say that, that the boundary conditions in the cross channel are very simple. Psi of sigma and 2t is the same thing as psi of sigma plus 2 pi and 0. And what this is depends just on the sector we work. Right? Because this is now minus 1 in the NS sector and plus 1 in the remote sector. So what have we concluded? We've concluded that closed string exchange in the NS sector, though the diagrams representing closed string exchange in the NS sector, emerge entirely from the one-loop partition in the NS sector in the open string sector. Whereas closed string exchange in the Raman sector emerges entirely from open string one-loop partition functions in the Raman sector. For this multi-structure. Is this clear? Okay? So, if we are interested in computing the closed string exchange in the NS sector, we should just keep track of the NS sector. However, as we've alluded to before, whether we do the calculation in the NS sector or the Ramon sector, we get the same answer. And it's a little easier in this case to do the calculation in the Ramon sector, basically because we don't have to keep careful track of the imaginary phases that we get acting on oscillator states in the identification. As we've seen in NS sector oscillators pick up imaginary phases. Okay, so just for partly for variety and partly because it's easier, partly because this is the calculation version 2 does easily get this final answer. We'll do this calculation this time in the Ramon sector. We will look at the contribution of Ramon sector exchange in the first channel. That, as we said, comes entirely from the Ramon sector in the open string. And here there's a new element. See, because we're working with the Ramon sector in the open string, there are no 0 point energies here. Right? Because of supersymmetry. Okay? So here the leading contribution will be like what you get from close to exchange. Anyway, so let's work it out. So what we want to do is work with the Ramon sector. So this Ramon sector business, how does it go? We get one term that is so this Ramon sector with -1 to the power with no insertion of -1 to the power n. That gives us a factor of 16 from the 0 volts. It then gives us a factor of since we're in the Ramon sector, we're supposed to put a factor of -1 to the power n for the nth oscillator. Okay, so we have 1 minus 1 to the power m q to the power m, and this thing should be the power. Plus. Okay? What? All oscillators contribute. There's no doubling here. This is just the open string. It's just one oscillator. All oscillators contribute, but the mth oscillator contributes with the sign -1 to the power because of the omega relation as we work. Okay? Then there's the part from the Ramon sector with the sector with -1 to the power, with the insertion of -1 to the power. Okay, what do we get from there? So here we could get trace m, and then 1 minus -1 to the power n q to the power n. But what should we put here? What's the equivalent of 16 first? You know, when you ask a question like this in a lecture, the answer is always right then. The answer is 0. Tell me why. That second thing was in the Ramon sector with its trace of -1 to the power f times omega times q to the power a, q to the power l is 0 in the Ramon sector. Where did 16 come from the first time? $16 was 2 to the power 4. Where did it come from? The Ramon vacuum, the 0 volts. Now, what is the trace of -1 to the power n on Ramon vacuum? -1 to the power f is 1 on the chiral spinner, is -1 on the anti-chiral spinner, so it's 0. This is 1 plus 1 to the power 4, this is plus 1 minus 1 to the power 4. This is 0. Okay? So this term doesn't come. Okay. Is that clear? We would have seen more of this happening and we been working more with the Ramon sector. We've been focusing on this. The diagram of the Ramon sector with the minus 1 to the power n always is the same. It was very simple. Okay? So now we have to take this object, combine it with what we got for the bosons with the same diagram. That's the factor of eta to the power 1 over eta to the power 8 times z00 to the power whatever it was, with double arguments. You remember we worked with that last class for that? Just the bosonic partition function for both this term. And this term can also be written in terms of the z's. So that term, let me write it out, is z, this term is z01 2it times z 10. Can somebody explain to me why this is the case? To the appropriate power. So Z01, let's read it out. Z01 is NS sector with a minus 1 to the power n extension. And Z10 is Ramon sector with no minus 1 to the power.
Yes, and there is this Q which converts
Q to Q squared.
Q to Q squared.
Good. So this term would be what? It would take all even Q's and make them appear with a plus sign. Right? So we will have 1 plus Q squared into 1 plus Q4 into 1 plus Q6.
Which are the alternative terms?
Which are the alternative terms? What about this guy? This is the NS sector with a minus 1 to the power n. Because we got this doubling, instead of the energies being half, 3 halves, 5 halves, it's 1, 3, 5. Because the minus 1 to the power f, every term contributes with a negative sign. Okay? So that means that gives you all the odd terms here with the negative sign. Right? So this thing is just equal to that. Okay. Now I'm finished. Sorry. Okay, so now that we have this formula, we can play the game that we have. Now we've got the formula written in time. And that's actually combined with what we had for the bosons. Okay, so a factor of 1 over eta to the power 8 divided by z00 to whatever part we found last time. Now we play the same game. We've got this thing written entirely in terms of functions whose modular transformation properties we know. So we make the modular transformation. We look at the behavior under large S, and leave it as an exercise for you to check that this thing gives you a contribution to the dipole with a negative sign. Exactly as was the case for the bosonic string. And the relative factor is, so in normalization which we had 1 over 2 to the 5 from the cylinder and 2 to the 5 from the reclined bottle, this guy contributes to the factor which is 2. The relative factor for the Morgan string is just 2. Okay, this again the algebra is very similar to the bosonic string. Okay. So far we've worked without Champing factors. I'm sorry, this is minus 2. So far we've worked without Champing factors. We add Champing factors, we get a factor n squared from the cylinder, if the n squared is Champing factors. the factorial n here exactly as per the bosonic string. So the net contribution is 1 over 2 to the 5 into n minus 2 to the 5. 2 to the 5 plus minus n, the whole thing square. Plus is for SON, minus is for SPN. No, minus is. Minus is for SON, plus is for SPN. And so, the net result is that that goes cancel. And the gauge movement. Okay, the talk now starts. We terminate this. But okay, we've completed our discussion of the open superstring. Thank God. Next class we will begin a discussion of the Okay.